Welcome to Verilab's DVCon 2022 workshop entitled Proven Strategies for Better Verification Planning. Since the company's founding in 2000, we have helped many teams overcome the challenges of writing good verification plans. My name is Paul Marriott and I've been a verification consultant for more than 2 decades now. I'd like to introduce today's presenters, my Verilab colleagues Jeff Vance and Jeff McNeal, the Jeffs as we call them. Through the next 45 minutes or so, they will share their combined experience from working with many clients over the years. We hope their insights will help you better understand the verification planning process, and we're always here to provide consulting help to expand upon what we're presenting today. Many engineering teams don't make the time to build a verification plan at the beginning of a project. Often even managers don't see the value in such a plan, so aren't willing to waste time putting one together. Even if plans are done, they may not be kept up to date as the system changes during the development. As individual contributors, we may not have the freedom to create a plan for the entirety of the projects we're working on, but we may need to do a plan just for our own portions of the project. Scheduling a verification project can be a complex and inexact process. Most engineers do not have a systematic approach to the estimation of the effort of verification tasks. Some issues with the verification plan and process can make this task even more difficult. I will now hand over to Jeff Vance, who will begin to take us through the verification planning process.
So what exactly is the scope of a verification plan? There can be a lot of different opinions on this. For this presentation, we use the term verification plan to encompass all of these aspects shown here. Depending on your situation, some of these areas may be optional. First, we can plan the general scope of verification. For example, are we doing full feature verification or integration only? Is the primary strategy going to include both simulation and formal? Next, a key portion of the plan is identifying the verification requirements, looking at specific features and scenarios. Optionally, we can plan functional coverage at a high level, or we may choose to do this later. Another key area is a project plan. This is where we identify resources, a budget, and set a schedule. In some situations, it's a good idea to plan a strategy for verification and implementation. This might be a high-level test bench architecture and some guidelines for stimulus and checking. And finally, we plan which components are intended to be reusable. A plan can be captured any way you see suitable. You can use a single document, several documents, spreadsheets, or specialized planning tools. The ideas we're presenting today are meant to be universal. This presentation focuses on just the verification requirements and project planning areas. So we're going to cover the following topics in detail. We'll start with feature identification and analysis, and the second part of the presentation will cover scheduling, dividing work into deliverables, and organizing deliverables for linear progress. First, I'm going to present strategies for identifying features in a design. These are generic ideas that will apply to any design you work on. We've applied this approach to many projects to create successful verification plans. So the first thing is to ensure we have the right mindset as we analyze the design and create our plan. The most common pitfalls we have seen come from a test bench-centric mindset. We should avoid thinking about how we will verify things, and instead focus on what is required to be verified and why. Test bench implementation will come later, after we're done creating the plan. Avoid planning around test bench components you might have in mind. Our focus is on the design functionality, not the test bench functionality. Avoid planning too many details. Excessive detail creates too much work in the planning phase, and they're also likely to change. Avoid test lists, since these are an implementation decision. Instead, identify the key scenarios to verify. We can later decide how these scenarios will be reached by a test suite. And finally, if you decide to do coverage planning, don't specify all the specific bins. Focus on the high-level coverage goal, estimating the kinds of bins, like do we need a min, a max, maybe a few bins in the middle. The details of exactly what values these bins will be, we can decide that later during implementation. So with this mindset, we can proceed to analyze the design using 3 steps. So step 1 is feature isolation. Step 2 would be to classify the scenarios. And third, we'll inspect the plan for weaknesses. Feature isolation is an exercise where we isolate our focus to a specific portion of the design to decide what we're required to verify. A common way most people do this is to take the design spec and break it down by section. Another way is to analyze one RTL block at a time. We can then look at large-scale features that concern many blocks working together. We can isolate real-world use cases. We can also isolate portions of the design that are more complex and have a higher chance of having bugs. And we can isolate special cases like corner cases and stress cases. As we isolate these features, they can have dedicated sections in our verification plan. This will help keep things organized. The key point is it isn't sufficient to break down a design just by a spec or a block diagram. We need to apply all of these different viewpoints to create a stronger plan. Here are some examples of what this might look like. In this design, I've highlighted several isolated features in yellow that fall into common categories. We can first isolate each interface, focusing on planning how we verify the protocols. Next, we can isolate the data flow between interfaces. In this case, we're only concerned with how we verify the propagation and translation of data. We also use interfaces to access registers, but register access is another isolated feature where we focus only on the permissions to read and write registers. Then another isolated concern are the features controlled by these registers. The key point is, in reality, nothing is truly isolated in the design, since all these features work together. But by isolating our focus to each perspective, we're less likely to miss anything. We can then plan various mixed scenarios by analyzing how these features work together. It's also sometimes a good idea to have sections where we're planning on using a special strategy or tool, such as formal verification on select blocks, or white box concerns that probe into the design. Other types of features we can isolate are transaction types, transaction flow patterns, configurations, and timings. We don't have to plan out every possible mixture of these features, but we can plan the most critical combinations to verifying the design. These can include mixtures of configurations with timings and various transaction flow patterns. It's easier to think of these interesting combinations once you have already thoroughly analyzed the isolated cases. Another important section in your plan should be for legal exceptions. These are the weird cases that aren't part of normal operation, but they can happen and they're supported by the design. Examples are soft reset, protocol errors, and FIFOs getting full. You should also have a section for illegal scenarios. These are completely unsupported by the design, and the spec must say that these are unsupported, so it's clear to the end user application that they're forbidden from ever attempting these. However, you may still want some tests to stress the design with these scenarios. This depends on the type of product and the domain you're working in. Examples would be verifying that the design ignores illegal inputs or can recover with a reset. It's common for engineers to confuse legal exceptions with illegal scenarios, so this is a key area for us to find bugs. This often happens because there's often ambiguity in the spec, and designers often make assumptions around these cases. So there are 4 benefits that we have seen in our projects by applying this approach. First, the test bench implementation usually goes faster. The plan influences how we structure the test bench and write our code. The solutions are more organized, less complex, and we avoid work duplication. For example, we can design our UVM sequences with control knobs that align to the plan. We then use this to provide nice APIs for controlling any mixture of features we need. We also experience better communication. It's easier to report status to management and collaborate with the design team since our plans are based on design terminology. We don't have to confuse people with test bench terms like agents and scoreboards. Better communication also means new team members get up to speed quickly. We can also review and close coverage more easily. We also have more flexibility to adapt to problems during the project. We can adapt to design changes quickly. We can isolate bugs so they don't block progress when we need to verify other features. And finally, we can create more accurate schedule estimates, and this will be the focus of the second part of this presentation. The final step is to inspect our plan for weaknesses. A good way of doing this is to review every item in the plan and ask ourselves 3 types of questions. We check correctness by asking, is this valid? Check precision by asking, is this specific enough? And check completeness by asking, is anything missing? The key strategy here is to avoid ad hoc thinking. Ad hoc thinking is more random and tends to rely on luck for us to think of everything. This creates schedule risk. We may need to rework parts of the test bench later, and we might miss some important scenarios. In contrast, a checklist of questions gives us a more structured approach to evaluating the plan. These types of questions direct us to the weaknesses, and our analysis is more organized and consistent across all the features. So examples of checking correctness would be to ask, is this technically possible? Does the design really implement this option? It might be a standard protocol, and the design only implements a portion of it. Is the behavior fully specified? Do the RTL parameters allow this option? It could be that there's reusable IP inside this design with features that will always be disabled. We can also ask, do we care? Some features might be technically possible, but they aren't valid use cases for the end application. And are we getting too detailed in our verification requirements? Some details may not actually be important to verifying the design. Checking our precision is also very important to avoid problems later in the project. If we're vague in our plan, people may later misunderstand the intent of our tests. Don't just say, verify we can drive transactions into the design. What is the specific reason for driving transactions? Are we verifying how they are processed, or if the data flow is undisturbed by other events? Are we verifying values, timing, access rights, throughput, resource contention? It's also important to ask, what is the context for this feature? Under what conditions are we verifying this? What are the dependencies? Are there any disqualifying conditions where we don't verify it? And if so, do we have to verify something else? Are there other contexts that exist that we completely overlooked? These kinds of questions are very likely to reveal scenarios that were overlooked in the initial plan and aren't called out in the spec. The final assessment is, did we leave anything out? One way we can do this is for every feature we wrote down, create a list of influencing variables and ask how can that variable change? What is the impact on that feature for every change? Is there a new verification requirement not already covered? When we review each scenario, it's also important to ask both what do we expect and what don't we expect. It's possible we overlook things we need to verify don't happen. And finally, we can double check the cross concerns of all the isolated features we identified. Categorize all the different major combinations of features, and then categorize all the unique outcomes from those combinations, and look for any new verification requirement we may have missed. So hopefully you're getting ideas for how you can apply this approach to the designs you're working on. I'm now going to hand it over to Jeff McNeal, who will present how to create a schedule to meet the verification requirements.
Most verification teams and many design teams seem to do a terrible job of scheduling the verification effort. This often leads to confusion on the larger team about the state of the verification work and an inability of the project to predict how much longer the verification effort is going to take. In my experience, these problems stem from a few planning failure modes. The first failure mode involves too much planning in too much detail too soon in the process. The second mode involves not doing enough planning or doing no planning at all. The third mode can be more subtle and involves focusing on the wrong things during the planning process. The too much too soon method is usually a good faith effort to do a complete schedule. Detailed lists are often made, coverage points, assertions, stimulus plans, class lists, etc. Often a test bench architecture document is needed to plan all the details of what is going to be done. Once all this information has been gathered by the team, schedule estimates of each item on the list are made. This can be okay if we have detailed and finalized specifications for exactly what is going to be built to ensure that there aren't going to be any changes. If, however, we're dealing with draft specifications or protocols that are still in development, much of this effort is likely to be wasted. This process can be very time-consuming if the project is large. It's also very difficult to estimate the effort required for a single task in isolation. If people on the team have different assumptions about what is included in each list item, estimates can differ wildly. The team ends up spending a lot of time putting together estimates for each line item, leading to a huge list of small tasks. One pitfall of this type of methodology can be that while each list item has an estimate, there are a lot of infrastructure tasks that need to be done but aren't included as an item on any of the lists. This list needs constant care and feeding. Updates for every status on every item that is finished, updates for new items, updates for deleted items, updates for changes to features. Ironically, this level of detail doesn't do a good job of communicating with the rest of the team, especially if we haven't organized the list in some way that's easy for outsiders to understand. This can lead to frustration on the verification team about wasted effort and abandoned plans. The team may spend several weeks at the beginning of a project put together a detailed plan that ends up being abandoned. Ideally, we like a plan that doesn't require so much maintenance. Problems associated with the too much too soon methodology often lead engineers and teams to adopt the opposite approach. I've been on a number of teams that have insisted that trying to put together a schedule is a waste of time, and we needed to get started with real work instead. If nothing is given to the project manager to use for progress tracking, they will often come up with something on their own. Sometimes this is the number of tests finished, sometimes it's some sort of manual methodology that doesn't take into account how verification works. Sometimes this is a proxy for progress, like a coverage number. Coverage is a great way to figure out what is being missed or to detect that a change has an unintended side effect, but it's a terrible way to predict how much longer things are going to take, especially when we remember that the percentage can go down when we add more coverage points or more RTL. If you've ever spent a meeting explaining why the coverage went down again, it may be because somebody's using coverage as a proxy for progress. This methodology leads to frustration about the status and scheduling on the verification and project teams. Those not in the verification team don't have any idea what's happening with verification and often begin to ask for more and more details about who is doing what. We want a methodology that can better communicate our status and Another failure mode is to start building the test bench architecture in detail and then estimating how long each of the test bench blocks will take to implement. This can work much better, but introduces the extra step of needing a detailed architecture of the test bench before scheduling can begin. If the team has finalized specifications that aren't likely to change, this can work just fine. If things aren't finalized, then working out architectural problems very early in the process requires knowledge of the DUT that the team doesn't have yet. When the inevitable changes come, all the architecture and estimates are now out of date and not useful, or the work has to be repeated. It is appealingly simple to take all the blocks of the test bench, like the monitors, drivers, sequences, checkers, and coverage points, and then estimate how long each of those should take to implement on their own. Experienced engineers may do a good job of estimating effort for blocks, especially if they've done something substantially similar in the past. However, problems often arise when we're trying to communicate our status. We can't develop a single test bench blocks by themselves. They need the blocks that they interact with to progress along at a similar rate. If there are more blocks than engineers, then partly finished blocks need to be left in order to work on other test bench components. None of the blocks can be truly 100% finished until all the blocks that they rely on are also 100% finished. We're all familiar with the 80-20 rule, but how do we apply that in a predictive manner? How do we determine how much effort or time is left when a block is 80% finished? This difficulty is compounded when people aren't working on a block full time until it is finished. One pitfall of this method is that any changes to the design or protocols actually change the amount of work the verification needs to do, but those changes are rarely reflected in the schedule estimates. We would have to go through our list of estimates for every affected block and then revise its progress downward by some amount. If the project manager is constantly begging the verification team to just tell me what's done, or you told me that that was already finished, your team is likely too focused on the test bench blocks. This often leads to frustration about status and scheduling on a verification project. We want a solution that can better communicate our status and predict end dates. One of our goals for the scheduling process has to have a way to clearly communicate the status of the verification effort. Communication with the project team and within the verification team is important to a project's success. One important thing to communicate is the status of the verification effort. Things like, what have we verified? What is left to be verified? Are we on schedule? When will we be finished? These sorts of questions are going to be asked about the verification effort on a regular basis, whether we like it or not. If we don't provide direct answers, then the folks asking the questions will either draw their conclusions about progress, or look for answers in other places. So how do we do the scheduling exercise so that we can get results with less effort? How can we set up the schedule so that we can clearly communicate the status of the verification progress? How do we produce a schedule that adapts to changes without having to expend a large amount of effort? Well, there are a lot of ways to improve your team's scheduling abilities, but we'd like to focus on two that get a lot of benefit with very little effort. When these two methods are used together, they can make a huge difference in how much time is spent doing scheduling and how effective and useful that schedule is. Neither of these methodologies require major change to the verification or project management process. They're mostly mindset changes that relate to how we think about the scheduling process. We found it is much more effective to divide the features we're going to verify into groups of related tasks and features, which we're going to call deliverables. And then we can work through the process of estimating and scheduling those deliverables so that we can provide a linear progress. For today's discussion, we're going to use the term deliverable to mean a bundle of work that the verification team will deliver to the project team. These are sometimes referred to as internal process deliverables or milestones or phases. A well-constructed deliverable has three main components. First, we need to define what this deliverable is going to do and how the team will know that the deliverable has been completed. This is our definition of done and is used to determine the second part, the list of tasks and work that needs to be done in order to complete this particular deliverable. Once we have that, we'll be able to estimate how long it will take the team to complete the deliverable. As we get started planning a verification effort, we want to divide the work into about a dozen deliverables. It's a handy number to work with early on in the verification effort, as it is enough to provide detail and specificity, but not so many that they aren't easy to keep track of. In my experience, too few deliverables leads to things like half done, 80%, 100% style deliverables, while many more leads to lists of hundreds or thousands of deliverables that are hard to manage. One of the most important and often misunderstood aspects of a good deliverable is the definition of done. Believe me, I spent 20 years of my career doing this part completely wrong. The definition of done is how the team is going to communicate what this particular deliverable is all about. It tells those outside the verification team what the team will deliver so that they know what to expect and when to expect it. It helps the verification team limit what is included in the deliverable and focus what they're going to work on to make sure that the deliverable is complete. Therefore, a unique definition of done is required for each deliverable. A generic definition doesn't work. When writing definitions of done, it can be useful to think of what new thing the test bench will do rather than what state the test bench will be in at the end of a deliverable. Will it execute a new type of transaction? Will it check a specific feature, perform a type of test? This is different from describing the state the test bench will be in terms such as half done or coded but not checked in. The definition of done should ideally be a single action that involves a whole test bench and not a long list of smaller separate actions. When writing definitions of done, it is important that we don't conflate having a feature completely verified with a deliverable being done. For example, we often think that the verification of a feature could only be done if we finished all the various aspects of the verification under full random conditions. While there's nothing wrong with that, often a smaller or partial deliverable can be just as useful. We may want to limit some of the degrees of freedom or features that we're verifying to make the deliverable smaller. In the case of the definition of the done for the deliverable isn't that the feature is completely verified, but that some aspects enumerated in the definition of done have been verified. It's all too common for teams to come up with some sort of procedural definition of done that involves revision control status and passing tests, and that is the same for all the deliverables. These sorts of definitions don't tell anybody anything about what has been verified when a particular deliverable has been finished. A state can be very hard to nail down and can also be hard for outsiders to really comprehend. Are we partially done in terms of lines of code, of functionality, of calendar time? So here we have some examples of poor deliverables, definitions of done on the left in red, and much better definitions of done on the right in green. It can be very helpful to clearly define how a deliverable will be demonstrated. By keeping the focus on a demonstration, we're keeping the focus on what is actively being done rather than on a state of being. Most often this demonstration will be a test or a set of tests. We're not advocating a directed methodology, but having a single test to point to as proof that a deliverable is finished can be very useful. Sometimes it can be useful to have other non-coding tasks as deliverable, such as a completed architecture document, an automated coverage reporting, or test bench documentation complete. Now that we know what done means for each deliverable, we need to come up with the work that we'll have to do in order to demonstrate our deliverable. At this point, we want to get a list of things that we'll have to do in order to satisfy our definition of done. If this is the first pass in the defining phase, we may need to keep this to a high level to be refined later. The goal at this point is to get a comprehensive list of what needs to get done, paying special attention to different types of categories, such as the test bench work, such as the environment, assertions, adding coverage, agent updates, etc., and the project infrastructure work. Maybe we have to update scripting or write a behavioral model, or generate reports. We want to do a breadth first list, making sure we don't let any types of work slip through the cracks. We don't need to list every assertion or every coverage point individually, but we should have an idea of how many there are for a deliverable. It's important to remember at this phase not to include anything that isn't necessary for our demonstration. It can be especially helpful at this stage to critically look at each thing on the list and determine if it can be moved to a later deliverable and still satisfy our definition of done. It's perfectly acceptable to implement only these portions of the test bench that are strictly necessary for this deliverable. Let's take a look at an example. For this example, we've decided that our definition of done is a test which encrypts one AES transfer. Now we can make a list of what has to be done in order to complete this deliverable. We're listing the functionality we'll have to add to the test bench in order to complete our demonstration. At this point, we're assuming a UVS-M test bench for simplicity's sake. Notice that we aren't going into details about where or how we'll do the work, just getting all of the changes we'll need to make gathered into one place. This test bench will have to encrypt and decrypt data packets. This may happen in a sequence item, it may happen in a scoreboard or a predictor. At this point, it doesn't really matter where it happens. The process is essentially the same. We'll decide later where this happens. Right now, we're only listing the work that needs to be done. We'll need a few new sequences to handle key generation and programming. We've chosen to include coverage in this deliverable. We're covering the DUT modes and some coverage of the keys as well. At this point, we're assuming that scripting to merge coverage and generate coverage report was finished in an early deliverable, so we're not including it here. Notice that we haven't enumerated all the coverage points, just the major categories of what we'll need to add. If we've done all the steps up to this one correctly, we'll have a nice bundle of work that we can use to make an effort estimate. We're going through a rough estimate here and sanity check the overall schedule and tape out date. It shouldn't take more than a few minutes to estimate most of the tasks at this point, but some of the more complex ones might take more thought. We aren't looking for a down-to-the-minute estimations at this point, and for larger projects, we may want to just stick with task granularity of a week. Avoid the temptation to start doing architectural or test bench design work at this stage. If there are big decisions to be made before pieces of work can be done, include time to make that decision in the effort estimate. To continue with our example, let's add some estimates for each of the line items in the work list. Each deliverable has a clear starting point. The previous deliverable had a clear definition of what work would be done and what was done when the deliverable was finished. In this example, we already have working self-checking traffic, so we're simply adding the encryption functionality. Each deliverable also has a clear endpoint, our definition of done. And we're estimating relatively small chunks of work, about 2 to 4 weeks, ideal. So this task can be fairly straightforward. In this example, let's assume that the team needs to learn more about AES, so include that time in our AES encryption and decryption estimates. Since we've been shooting for a dozen deliverables, doing effort estimates for all of them should only take a few hours or maybe a couple of days. Once you've finished the complete set of deliverables with their definitions done, their task lists, and their effort estimates, we can review this rough draft schedule with the major stakeholders to sanity check the schedule. Because of the language we've used, it's easy for those not on the verification team to understand what we'll be working on and when. We can anticipate issues that may come up, such as the design team not being ready with the RTL by the time that we're planning on doing the verification, or validation needing an early version of a particular feature by a specific date. To continue our previous example, we can check with the design team that the AES encryption will be in place when we want to start doing the verification work for it, or that the test bench support will be ready when the design team needs it in place, whichever model your development uses. Since the deliverables are fairly independent at this point, it can be simple to swap their ordering around. We can also tell the team when it can expect from the verification at a specific date. After dividing things into deliverables, our second recommendation for reducing effort and increasing effectiveness is to organize the deliverables for linear progress. So what do we mean by linear progress? The deliverables should all contain roughly the same amount of work. We don't want to end up with 10 deliverables that take a week and then 2 that take 6 months. We want to be delivering something on a regular and predictable basis. We've all seen the graphs that show how coverage-driven, constrained random verification gets done faster than a directed methodology. These are a few that popped up when I did an image search for constrained random coverage-driven verification. These graphs are not wrong. That methodology can result in a shorter duration project and is a valuable tool in our arsenal. These graphs usually gloss over the fact that the final target coverage that is being approached is a theoretical final number. Early in the project, we don't actually know how many coverage bins we will have at the end of the project. That number tends to grow at the beginning and then shrink a little at the end. Expressing the target as a percentage further obscures the fact that we're actually comparing two integers, what has been hit and versus what has been coded. The coded portion has to grow over time as the team does the work to code the coverage points, or the RTL team adds lines of code. If we take a snapshot of the curve partway through, it usually doesn't look anything like any of these curves. Our target or maximum coverage may not be close to the final coverage. Our covered progress may or may not relate to what has actually been verified up to this point. Where we run into problems is when we try to use those graphs as prediction or tracking tools. They're always drawn as a monotonically increasing curve, whereas actual reported coverage may have drastic spikes and dips as more coverage points are added to the total. In real life, we have to deal with changes in the denominator of a coverage percentage number. If we try to use coverage metrics as indicators of status, then the ideal coverage curve, with its big jump some point near the middle, starts to look an awful lot like magical thinking. It starts to look to outsiders like the team is confidently predicting that everything will suddenly get easier, or everybody will suddenly be more productive real soon now. The ideal graphs also show that at some point in the project we get a big jump in coverage, but they don't ever really label exactly when that jump will happen. When we're trying to report status, if we're nearly 50% of the way through a project, how much more time until that huge jump comes? As we're approaching 80% of the way, how can we predict how much time coverage closure is going to take? There's nothing wrong with graphs like this, but they're not useful in predicting the future or determining verification status. They're tools to sell a coverage-driven methodology. We need something else for scheduling. When we can't easily communicate where we are and how much longer things will take, it can result in a loss of trust or confidence in the verification team. It's helpful to be able to demonstrate progress against the plan to those outside the team. This helps build confidence in the team, helps identify what has been finished and tested, and helps predict how much more time will be needed to complete the plan. In this example, we have added the purple line, which shows the deliverables are being checked off over time in a linear way, as opposed to the rapid increase predicted by a coverage number. When the verification team makes a scheduled deliver functionality on a regular basis, it becomes simpler to determine if those commitments have been met. In addition to communicating with the project manager and the rest of the team, we'd like to not have to spend a lot of time tracking our progress. Instead of relying on a metric that are not good predictors, we should use a metric that does have value predicting. In order to make our deliverables easily usable as a schedule, we need to do a few things. One is to realize that the team should be working together on the same deliverable as a group. We want to start a deliverable to work on only that deliverable until it is finished. This allows us to check whether or not our estimates were good, and allows us to report a deliverable as done in the way that we don't have to come back and revisit it. Another is to make sure that our deliverables are fairly consistent in the length of time they're predicted to take. This serves several purposes. It helps linearize the verification progress metric. If we start off with several small deliverables and then a huge complex task that'll take a long time, we lose traceability. Second, as we divide up the larger and more complex deliverables, we make it easier to do a better job of predicting the effort that they will require. When we're doing a quick first pass like this, the bigger deliverables are often where the large portions of the work are, and by dividing them, we force ourselves to do a more detailed analysis of them. In order to do this, we've got to pay some attention to the ordering of deliverables. Our first deliverable will be starting off from scratch, and later deliverables will build on what we've already finished. There will, of course, be a lot of factors that affect the order we can finish deliverables. Most of these will come naturally to the team, things like the internal test bench dependencies, availability of RTL or external IP, and the priority of the various features. Some other things to keep in mind are the timing of what we're delivering to external teams, like back-end or firmware teams. Some projects may want to focus on a depth-first approach, where features or interfaces are completely verified before the team moves on to another feature. Other projects may want to use a breadth-first approach, where a basic implementation of each test bench feature is finished for all of the interfaces. When that's done, then the team could go back and add more complete support and verify the features fully. Either approach is valid and doesn't affect what we're talking about. By sticking to working on a single deliverable at one time and completely finishing it before we move on to the next, our status reporting becomes very low effort and clear to the whole team. A quick comparison of what is done versus where the team thought they'd be tells the project manager whether we're on track or not, and even better, how far ahead or behind we might be. The team can provide finer grained status by estimating how far ahead or behind they are on the particular deliverable they're working on. It doesn't take much time to figure out if you're ahead or behind on a deliverable that's estimated to take a couple of weeks to finish and you're in the middle of it. It also is easy to determine what hasn't been done, but more importantly, we can easily make decisions with the team about the order of future deliverables. One of our goals for the scheduling process was flexibility, to quickly update the schedule when things change. We'll inevitably have changes after the project starts. On some projects, these will be small tweaks. On others, they can be major and disruptive. I've worked on projects where we start off work before the full architecture has been finalized or before third-party standards have reached the 1.0 stage. When new features or major changes come along, we recommend adding a new deliverable to the plan. The deliverable will contain the parts necessary to handle the new feature or change and should go through the same deliverable work and effort estimation process. This helps to communicate to the project team the impact to the overall schedule of the change. In some cases, changes to future deliverables can be easily absorbed in the existing schedule without any impact, especially if detailed planning for that deliverable hasn't happened yet. And the change doesn't add a significant amount of verification work. For example, adding or deleting a control register for a feature that hasn't been implemented yet shouldn't change the overall deliverable. On the other hand, adding a new encryption mode will have a huge impact on the verification effort. By packaging the impact to the effort and schedule directly stemming from the change, we can communicate this impact with the project manager in a way that's easily understood. We've had cases where the team decided to remove a change that had already been made to the RTL because of the impact to the verification team's schedule. Our suggestions here are flexible enough to work with different planning styles and project situations. The style fits in well with agile development methodology, but doesn't require it. Some projects need to be completely planned in detail before any work commences. We can still use deliverables at a higher level of abstraction to work out a rough schedule and for reporting of status. If necessary, we can perform a detailed planning of every deliverable before we begin test bench coding. On other projects, verification effort has to get started before major features, let alone details, have been solidified. For these kinds of projects, we can work out the detailed plan for each deliverable as we begin to work on it, sort of a just-in-time scheduling. This flow will work at either end or anywhere along this spectrum. By grouping work into deliverables and then focusing on those deliverables as the fundamental unit for verification scheduling, we greatly reduce the number of units we need to work with when planning. Performing the first pass of estimation and scheduling should only take a couple of days. More detail will be needed as we begin to work on the deliverables, but that work can be done after a rough schedule has been produced and reviewed. A well-defined set of deliverables provides several advantages. It raises the abstraction level of the process, reducing the effort required. It improves the communication among the team by clarifying what will be done and when. As we're communicating deliverables that have a set endpoint related to a design feature, the larger team has a much better idea of the status of the verification process. This also reduces the effort to keep track and report the verification team's status. For large or complex projects, we may need to further divide our deliverables. This can be done early in the project if the information is available, or it can be postponed. It can be quite effective to delay detailed planning until work is about to begin on a deliverable. At that point, we have a much better idea of what the actual requirements are and the state of the RTL and test bench. We can also take advantage of the knowledge that the team has gained during the process. Deeper knowledge of the spec and protocols can greatly simplify task enumeration and effort estimation, especially if the protocol or design specifications have matured. This type of process can be implemented at various levels. The verification team doesn't need buy-in from the design team to structure their schedule this way. In fact, I've used this process on my own assignments at clients without buy-in from anyone. One of my favorite advantages to this method is that it's very flexible. Deliverables are mostly independent of each other and can quickly and easily be moved around so that they start.
Thank you for attending our DVCon workshop. If you're watching this live at DVCon 2022, myself, Jeff, and Jeff are here to answer your questions. If not, if you need help creating verification plans for your projects in the future, don't hesitate to contact Jason Sprott at jason@verilab.com, and we'll be happy to schedule a consultant to help work with you. Thank you. So thank you to everybody who attended. As I said in the closing slides, Jeff and Jeff are here to take questions, so feel free to ask away.
Come on, Bruce has got to have a question somewhere.
So Greg Tumbers just wrote, any suggestion on how to write design device specs that make it easy to plan the verification?
Jeff, you have any thoughts on that? It's a good question.
Yeah, it's a good question. I think, it helps to categorize, features and sections that help us start planning out, our verification strategy. But I think it's important to allow some iteration and collaboration there, because people will have questions that will need to be reflected back in the spec. So any sort of collaboration or iteration there in having a nice strategy for how to categorize things in the spec in a meaningful way, so it's easy to review things, can help. But
and as somebody just pointed out, I think doing your spec in a little bit more of a requirements style, the design shall do this, makes it fairly straightforward to move that to a verification plan.
So Horace just asked, what is your opinion on requirements tools and how do we use these to link the requirements to the test plan? Of course, this is the $64 million question.
Yeah.
Yeah, it is a tough question. So I've seen environments where, people have separate requirements tracing tools, requirements management tools that are done, outside of a verification plan, and find ways to kind of trace your test bench back to those requirements. And so that is something that can be done, but it's definitely more to set up that kind of flow. And plenty of us can get by without that. I mean, there's still some value in being able to capture your verification requirements in a kind of some sort of explicit format, even if you don't have the fancy tools for managing and tracing them. Just being explicit in writing out your what is required to be verified gives us some benchmark to go against when we're doing the implementation. So yeah, I think if you're using those kinds of requirements-based tools, that's great, but we can still do a lot. We can still adopt a requirements mindset in our verification planning, even if we don't have those tools.
Mm-hmm. Early on, somebody asked about recommendation for how much time to spend on verification upfront. So where this really gelled for me just a couple of years ago, I was, we do contract work. So I was at a client and I only had a week of overlap. So I showed up on a Monday and their engineers were all going on holiday the following Monday. So we had a week to put together the first draft of the plan and ended up getting it done. So from setting foot in the door, hi, my name's Jeff, getting a laptop, getting the documentation, we had a first draft verification plan with, there were 12 deliverables before Friday morning, so that we actually had already reviewed it once with the client. And it was intended to be, I think, a 9-month engagement that ended up lasting a lot longer. But that's just, for example, it doesn't take that long to do the first, a first draft. And then the other thing that I'm not sure if everybody caught, you can, especially if you're in a situation where the specifications are changing, you can push some of your planning to later. And we did that at this particular engagement. We had a dual lane thing that we knew we were going to need a weird driver or agent to make use of. But we decided to delay figuring that out for 6 weeks until everybody was back from vacation and we had a better idea of how everything worked. And that was really effective in that particular case. I don't think the format necessarily matters. I've never seen one I like. I've used documents, I've used test lists, I've used spreadsheets, I've used each of the big three's recommended stuff, and they all have issues. So whatever your team is using now is probably fine. This is more about the mindset of the definition of done, what a deliverable is, and less about the tools to track it.
I think the content of the plan is more important than the format it's in, and getting teams to write the requirements and specification well in the first place is, I think, the biggest challenge.
Oh, how dependent should verification be on RTL maturity? It's really nice if RTL is done, but you don't have to. And that's where I think that's a place where this sort of methodology, or get a quick rough estimate or a plan put together first and then review it as the design matures. I think that's where this kind of a methodology works really well. If you just kind of know we're going to have this and then we're going to make that bigger, go. That's the kind of environment I've worked in a lot. Jeff has been in a different, more requirements-based environment in his career. So yeah, that's where if you don't have a lot of detail, then it doesn't make sense to spend lots of time writing out or documenting 8,000 coverage points you're going to write someday. There's a question for Jeff. Coverage model.
Okay, yeah, there's a question here. Yeah, how do you see the coverage model fitting into your planning methodology? So there are a lot of opinions on this. So some folks like planning your functional coverage up front, and some prefer not doing it up front and doing it later. And I think this is going to vary based on your situation and what you think is most important in terms of your schedule. But there is some value in doing some coverage planning up front at a high level. It doesn't necessarily make sense to plan out, every single cover point, every bin. That's way too much detail up front, because those details, you might not know them yet, or they might change, and you're going to spend a lot of time planning things that are later invalid. But what you can do is just plan, okay, we need to at least cover this feature. So we need a cover point for it. We don't know how many bins necessarily it'll be. We know we need a minimum, a max. We know we need to sample it at a particular time. So when you sample the coverage is usually a good part of the requirement, because if you sample at the wrong time, it means you didn't actually cover what you were supposed to cover. So a good high-level plan is just say, okay, we need some kind of cover point on this feature. We need to sample it at this time, and that's it. And then later at implementation, people can go off and implement the coverage model however they want, but they have that plan as their kind of reference of what they're aiming for.
I want to point out also that sometimes the urgency to do detailed coverage planning very early in the project goes back to this using coverage as a proxy for progress. If somebody's trying to use that S-curve to know when we're going to be done, or to predict the calendar date when we'll be done, then you have to have every single coverage point defined on day one, and you can't add any later. If you have a different way to track your progress, such as using deliverables, then that coverage plan isn't so urgently needed on day one. You can add coverage as you work through deliverables, as you do a detailed planning on a deliverable, when you're actually looking at what's going on, getting details out of the spec, the updated spec. It's much simpler to figure out what coverage needs to get done.
So Mark, if I understand your comment, deciding what needs to be covered can be done fairly well up front, but the how to do it can be deferred until later on, because it's not just sampling the coverage, it's making sure it's correct, the sequencing is valid. There's all sorts of things which go into validating that the coverage is actually relevant and appropriate, not just what it is you need to cover. There's many aspects to coverage beyond just the simple items themselves.
Mm. And to touch on what Dylan is talking about a little bit, where they say they prefer RTL to be working at the same time, so the RTL and the DV aren't off doing other things. By quickly producing this high-level rough schedule early on, you can align that with the design team very well. I don't know if you've ever put together a test bench architecture document and then tried to talk about that with the design team, or even worse, the architecture team. And their eyes glaze over when you start talking about scoreboards and monitors and things. Whereas if you say, we're going to work on the encryption, this month, and we're going to work on the IO drivers that month, and we're going to work on the bootloader this other month, you're all on the same page, you're talking the same language. And so it's easier to arrange things so that the RTL will be ready when you are, or vice versa. If the test bench leads, then you can have the test bench ready when the RTL guys are getting started on that. I also think that it's in the projects I've usually been on, I'm starting verification before the design team has even finished up detailed architectures. But if you are working on a project that does have pretty firmed up everything, it's perfectly okay to go through, do a rough schedule, and then the first deliverable is detailed schedule, and the second one is coverage plan, and the third one is test bench architecture. That's fine too. Bill, if you find any good open source test plans or test benches, I'd love to hear about them.
One of the problems with doing presentations like this is that most of the good test plans are, of course, proprietary to the clients we're working with. And so as much as we'd like to share the good ones and also the horror stories, unfortunately, we can't do that. I'm sure we've all seen the horror stories, though.
Yes. So Greg, I guess I'm not quite sure what you're asking, but
Sure. Why don't I just verbally do this?
That'd
So
be great.
what I'm getting at is, like, I actually think it's a great idea to try to develop verification prior to design, because then you think more about what stuff should do as opposed to going, well, I'll just make it match the RTL. I won't get in trouble with that. Right. So if you can would you schedule like a phase 1 deliverable where I have all my stimulus and coverage collection done, and then schedule a later on deliverable where I actually verify the block when the RTL is done?
Oh yeah, sure. That's the kind of thing that is useful. Like I said, I just kind of figured this out recently. And one of the things that we did is we had kind of a part 1 where we would put together stimulus and a couple of sequences of very basic nature. And so just write to the registers. We didn't even read them the first time through. And you can have that as a deliverable. Then you can hand that off to the RTL folks. So if you can get, in general, I found if you can get the designer some stimulus that they can use, they will often take that and run with it, and they will work out their own bugs as they're doing the RTL development. And
then they're not building their own throwaway test benches
that are
completely
weird, and then say, use mine, it's already done. Yes.
Yeah, sure. Okay, thank you.
And then we also had done so phase 1 is just a very limp along, almost does nothing. And then phase 2 does the main features you care about. And then phase 3 might actually be, okay, now let's add coverage, close coverage, make sure we have everything hit, add the assertion, whatever, right? You can then randomize as a later phase. And whether you do phase 1, 2, and 3 all at once, or you do phase 1 of each interphase first, and then come back and do phase 2, just depends on how your team runs things, how the RTL is developed.
Okay, great. Thank you.
Mm-hmm.
So we have about 2 minutes left. If anybody else has any more questions, we'll be happy to answer them in the remaining time we have.
Also, I believe there is a chat room. Is that correct? Maybe.
Yes, I will. Once you all finish up, I will share a slide on how to access GatherTown.
Okay. So I'd be happy to hang out there for a little while. GatherTown, there we go.
Great, thanks.
And there is a comment section on the website associated with this workshop, so you can put comments there and we'll answer them when we can.
And then Bruce, yeah, so that was one of the things that might have been in there. I might have taken it out, but formal verification, when you're planning a deliverable, you might say, oh, we're going to formal this piece, and you do that kind of a scheduling later on.
So I'd like to thank everybody for attending. I think we had a good discussion at the end here. And as we said, we'll be happy to continue this discussion in the GatherTown app. So once again, thanks everybody. Thanks, Jeff and Jeff. I think it was a very interesting session and certainly an area that doesn't get enough attention.
Yeah, thanks a lot.